Okay, so still non-zero as long as the count is above 0. We could proceed. Some of you might remember that we attempted to write an iterator, John and I and the rest of you. Of course, we put a couple of bugs here and there in the iterator. So let's take a look at what we did and where the bugs were. If Ryan would be kind enough to show us list pool, I'll show you where the bug was. And it was a tricky bug because it passed first round of testing. And of course, this Monday, there was some inexplicable behavior which I couldn't figure out what it was, and checked all the code. It was all right, but there was a bug in the iterator. Let us take a look what we had. If you remember, let us look at the function constructor, which takes one argument. Remember, this is a constructor which effectively does nil. We had a little tiny problem. Here, where now it says p.end, we said p.empty. And empty has nothing to do with list end. It's a Boolean indicator whether the pool is empty or not. Well, but, since you could always convert Boolean to an integral type, we did, and it worked, and whatever. So that was bug number 1. The second interesting problem, which I have to sort of show you, happened because, of course, we compiled, everything worked, if you remember, right? But then some people decided to use a different compiler. Specifically, Hernan decided to compile the code with G++. And he got a whole bunch of error messages, which he claims were not comprehensible. And I believe him. So what apparently happened is that we did not put word type name on line 147 and 148. And Clang thought it was perfectly fine. G++ disagreed. So what the issue is? So this is a complicated issue. Let me show you. I, of course, asked the highest authority in the world on language, and let us see what he answered. That's the email I got from him. First, I asked him, do I need, in this case, to put this type name, capitalized type name? And I got a very interesting answer. The answer is basically, it's allowed and recommended, but it used to be illegal, and now it is legal. That is not easily translatable message. That is, this is the quote from the standard. The significant thing is that it used to be type name was stupidly prohibited, were not required. So now it is allowed, but not required. Bjarne personally recommends it. So let me, at that point, when I tried to explain this message to Hernan, he said that he wished that somebody would explain to him why this type name thing is needed, which is a legitimate request. So let me try quickly to try to answer Hernan's question to the best of my ability. So let us look at the original situation. So once upon a time, there were templates, there was STL, people were writing code. There was no type name. And everything worked. But then, of course, clever people came, and you know where all the clever people reside? The standard committee, yes. So they came and said, look at this. If we have template, or actually let us lose automatic character recognition and things like that. Could we open a file called foo.x and write something there? So we write template class, as we used to say before typename, class T, and then we call it, let's say this is class foo, and inside class foo we say type def T : value type. Obviously, what you intend to do here is to extract value type defined in T and get it here. But you see there is some logic in what the standard committee people say. Let us try to follow their logic. Their logic says, but maybe value type in T refers to a static variable, which it could be. Of course, Hernan said, well, don't you know from the context that it's supposed to be a type? But they say, since they're oh so very well educated, they say, but that will make our grammar context sensitive. We need to figure out the meaning of a token without referring to it, the context in which it appears. So they came up with the following rule, that if you don't put typename, put a typename, they invented typename, compiler must assume that it is a variable, even if it is a type, right? To maintain this sort of property that you don't need to know outside context. Of course, the problem here does not really relate to the type name. Let us think where the problem, and anybody who knows me would know what I'll say, why the problem exists. Because the problem, of course, exists because T is not specified. The language has no concepts. For example, if we said container T instead of class T, could we? Class to container, capitalize it. If we had concepts. If we could say that, and if the definition of container would say that container is required to have an affiliated type, value type, then compiler could figure out what we really mean. So what often happens is that instead of solving the real problem, a partial problem is solved. So, of course, we still do not have concepts, so we cannot say container, but we now could say type name instead of class. So since they invented a new keyword, they said you could use it where we used to say class. Could we do it? So this is where type name got upstairs. It wasn't invented to be there. It was invented to say something is a type right here. Yes? So again, this is one of the problems. I mean, one of the greatness of C++ is precisely the language has been evolving for 40 years. One of the terrible problems of C++ is precisely the language was evolving for 40 years. Right? Sort of originally there were no templates, there were no idea of concept. Now we're trying to sort of put them in. Well, somebody else is trying to put them in. But you know, it works with all kind of quirks. So the advice Bjarne gives right now, put type name whenever you can to assure that it's a type, even in the context but it's not absolutely required, which is probably good advice because eventually it will be required in about 15 years from now. So, because that's how language developed. So, let's go back to the iterators because there are a bunch of interesting things we could do there. So, we talked. Could we? Yes. Could we go down to our iterator? So observe that iterator again is this struct. It's in general iterators constitute a concept. This is the word which you need to familiarize yourself at least before Bjarne comes, because he's going to in this class to talk about concepts, and unless you know what a concept is, you will not benefit. So again, let us think about what a concept of iterator is. How is it different from class? Anybody could say how a concept is different from class? Why couldn't we use an abstract class? C++ has abstract classes, like Java has interfaces. Right? Why couldn't we use something like Java interface, which in C++ is an abstract class, to specify iterator? This is an implementation detail. Ignore the implementation. So, yes?
Well, there's a number of issues, one of which is that when we have concepts, the model for the concept may not be able to derive something. So, for example, a pointer itself is a model of an iterator, but a pointer can't be derived from some base class.
Yes. But why couldn't we just use them to designate that this interface is an iterator interface?
Well, another issue is that some of what you want to say about a concept has some semantics that's not, there's no way to express it. It's saying this
Example. In case of iterator, what's the example? Even you actually goes not just semantics. There are some fundamental things you cannot do.
I'm not sure what you're thinking of, but for example, you need to semantically say that if you assign this to this, that these now have.
Ignore the semantics. Even at the interface level, it wouldn't work. Why wouldn't it work?
In abstract class, you can't say that a subclass has to define a type, right?
This is, first of all, if we try to make interface to the iterator as an abstract class, what happens with the value type? This operator returns reference type, say, which depends on the value type, but whatever. How could you do it? Abstract class, every function in the interface has to have fixed types. It could be int, ref, it could be something, but it couldn't be a reference type. Abstract classes or interfaces in Java are fixed set of interfaces. They describe identical interfaces. Here we're talking about similar interfaces. Right? The concept of a pointer doesn't define of iterator, does not define same interfaces. Star operator could return an int, or a double, or a container. Who knows what it returns, right? So it's a set of similar interfaces. There is variance on the types. This is first thing. The second thing, of course, is could we slide a little bit down? And look at how it's just a little bit more down here. It's going to be a bad problem. Because again, here, these guys define a binary predicate, a binary predicate cannot, I mean, in terms of interfaces, you cannot have binary functions. When you do inheritance, only the first argument changes, the second argument stays the same. So this is the second reason. But it's a lesser reason, because this reason could be fixed. In Java, they sort of fix it by always sort of doing casting back and forth. What you cannot, however, do is to fix the fundamental variance on things like value type. This is fundamental. All right? Yes?
Why can't the base class be a template itself defined in terms of a bunch of input types, like what the value type is?
The types you can, I mean, there might be a language where you could do that. But I do not know how to do it in C++. It is sort of, you have to, you know, without templates, you cannot get, I mean, inheritance does not allow you to do, I mean, sort of it's very hard to argue when people say, well, but couldn't there be a correct inheritance? Well, of course, the answer is yes, there could be a correct inheritance, but it's not what we have in C++ and in Java.
No, I mean, what I'm suggesting doesn't solve the friend function problem. I was talking about the previous problem, which is
Yes.
the fact that you need to return a specific type. Instead of returning a specific type, you could templatize the base class on the types that you're returning.
All the affiliated types. All the affiliated types, you would have template parameters.
No, no.
It's no longer an interface. You would have, the base class would be different types based on where you use it. So you couldn't use it as an interface.
The interface is an abstract, I mean, it's a class. It's not a template. Right? You say, if we make it a template.
Why does it have to, I mean, we started from the hypothetical of
Yes.
can we use base classes to define concepts?
No. Could we use abstract classes?
Could we use abstract
Classes as
Why
concepts.
can't an abstract class be a template?
Or it can be, but the two instances do not relate.
If I have abstract class X, and let's say it takes types A, B, and C, okay? X, A, B, C is a type. I can't just say X. I have to say X, A, B, C.
Yeah.
So you can't say returns X. You can't use X anywhere. You have to say X, A, B, C. So they're completely separate types.
It's the class that's specifying the concept that's the template. The thing that is returning, that again is we have to figure out how to
But
specify
my
those.
point is, you can't have now a function which says like for instance an iterator. I can't say I take an X. You have to say I take an X, A, B, C.
Yeah.
So you can't have functions that operate abstractly.
I see.
Okay.
Yeah, that's the magic.
So far, nobody managed, this is the simplest answer. So far, nobody managed, and we live in the world without concepts. For example, here we could not say when we write functions which take iterator as an argument, you cannot say what is requirements on the iterator. I'm just talking about type name. Now, so we know that there are several iterator concepts there. Input iterator, there's forward iterator, there's bidirectional iterator, there's random access iterator. There are some people who actually say, oh, that totally exhausts the iterator thing because that's what the standard is. And there's one great person who goes around, gives talks that Alex just named these iterators, 4 kinds, and there's no others. Therefore, you don't need concepts because there's just 4 different things. Some of you, I'm not going to name him because I get angry messages from all over the world that I'm insulting distinguished people in my class. So you figure out who the distinguished person is. So what I'm going to do now is to introduce new kinds of iterators, just of course to spite the distinguished person. But those of you who actually followed for example, this famous book, Elements of Programming, would observe that they were introduced before today's class. So let us slide down and look up. The first thing which we want to extend the concept of an iterator with a new concept of a linked iterator. So it is a forward iterator, which in addition to normal operation of forward iterator, which is plus plus, equality, and dereference, has one additional operation. The additional operation is operation set successor. What does it do? If you have an iterator and you have another iterator, you could just make the second iterator to be a successor of the first iterator. You could literally connect. Anybody understands what's the normal model? Linked lists. Right? Sort of as long as you don't do it, the topology remains. But you could move things. And of course, this is a very unsafe operation. You could do all kinds of things. For example, Hernan managed to create a circular list. And you can't, indeed, you could do it even with one iterator, by the way, by creating a little small circle list. But you can't do that. And some people say, this is very bad, it should not be allowed. We have to come up with the language mechanisms for not doing it. It's evil. These are these people who believe that there are some syntactic rules could make programming good. Are they right? Not yet. Why are they not right in case of circular lists? They're useful. Circular lists is a useful data structure. Sometimes you want to create a loop. Of course, if some uninformed person will take your list and attempt to get to its end, he will not be successful. For a while, yes. But it is a perfectly legitimate data structure, right? And it's a perfectly legitimate operation. Long time ago, when list existed, when Hernan and I were programming in Lisp, there were people who say you should never use replugd. This operation is called replugd in Lisp. And they were wrong. I mean, you should use whatever is given to you, but you have to be wise. Of course, could you write bad code with it? Yes, but you could write bad code with plus. Right? You could write non-terminating loops with plus. Just plus, nothing else. Right? You say, while true, a equal a plus 1. That doesn't terminate. So you say, well, let's not allow while true. Okay, so you write a equal 1, while a is greater than 0. A is equal to a plus 1. There are many ways of writing bad code, and syntax cannot help you. No syntactic restraint, no smart pointer will make a bad program into good programmer. It will just replace one sort of bugs with different sort. Bad programmers are very creative. They find all kinds of amazing things. So this is just one operation, right? So before we go further and look what else I added to our iterator. Yes? Let me explain, because I, in general, thought that there might be a situation where you will be reinterpreting, your iterator will be something like pointer-like objects. It will not even be a class. Right? So I don't want to depend, here it is, but in my interface I don't want to depend on new member functions. I'm just saying, okay, if I write I as an iterator, right now I could do plus plus this, I could do star I could write equality. I never write I dot something unless you refer to, you could use arrow to point to a field. There's no dot operator on iterators. So I decided this is, of course, a sort of personal call. So I decided to make it a friend. Then there is somebody who knows me better say, Alex, you're making it up. You just hate object-orientedness. I don't hate it, but I don't particularly like it. So from my point of view, if you have two ways of writing, you could write x dot foo, some function, or foo, foo open paren x. I claim the second one has one clear provable advantage. One fewer characters, guys. No matter what you say, it's one fewer characters. Plus, also, when I write generic code, so I always think, could it work on X, which is not a class? Could it work on built-in types? And the second one always can. It's just a function. The first one, you have to assume there is a class. And, okay, so, but if you make it a member function, nothing terrible will happen. You will have to type this extra character, and you will annoy me, but no, it's not, And object-oriented people will love you. Well, no, the object-oriented people don't do set successor. That is too dirty. So, okay, let us look at a function which uses that. That's the most basic function which we could have. Let us go to a file called listalgorithms.h. And let's look at this very, very important function, which is any Lisp programmer knows that reverse append is just so very, very useful. This is, of course, reverse append bang, or something like nconc with reverse, because it doesn't create a new list. It takes one list, another list, and does this. It reverses the first list and attaches it to the second list. It's very, very important list algorithm. Let us look at it. Okay? Here I'm, observe. I thought about using the spoon, but then I said, I'll just show you the code. But this is tricky. It's very simple, it's very, very important, but it's tricky. First of all, obviously, we go from first to last. I don't need to explain that part. No. So we go from first to last. Then we do a sort of, I was tempted to write I next equals successor of first, but sadly enough, successor is not a standard function. Maybe our friends on the standard committee will make it so, but is it? There's a function called next. Okay, so you could write next there, but I did it old-fashioned way. So first is next, and then I increment it. Then I set successor to the tail. I grab the first guy and set it, but before I set the tail, I create next. Observe that, there is a great temptation to do that after this. I've done it a million times. When you write code, you just say, it's not good, guys. You have to find the next value before you mutate the current. That is just basic of Lisp programming. And then what we do, now tail becomes first. We attached the first guy to the tail. And of course, first becomes next. Again, it's very tempting to say, oh, we don't need to do it here. We'll just put plus plus next here. Again, no, because at that point, it will be pointing to the tail. You will lose the list. It's a very, very important function. Yes? So the second function which we will look, it's our merge function. And this is we called simple. It's somewhat simplistic. We will figure out whether its simplicity is good or bad later on when you will attempt to measure it. But let us see, it's the same idea, plus it uses, of course, reverse at the end. So what do? We move along both lists, first range and second range. We move along. We check that they're not empty. If we're not empty, we find the smaller node. We do the comparison, and if the second wins, we make temp into the second and increment second. I do remember that I told you never use post increment. I do, guys. But I'm a sucker for certain shortness and prettiness even when I disapprove. Paul disapproves, but whatever. He wasn't present when I wrote it. So it will be 3 lines, So you see what we're doing on this line? Then, whichever one was the minimum, smaller one, we attach it to the temp. We attach it to the result. We're accumulating there. This is sort of like nil, but I haven't got nil, so I use last one as my pseudo nil. The amazing fact that I could write all good algorithms without having nil. As we shall see, I could write merge, I could write sort without knowing anything about nil. Just you give me some node which will function as a nil. Could be real nil too. It will work with nil. But that allows me, for example, to do the following thing. I could take a sublist and sort it, and it will point to whatever the remainder of the list were, if I do things correctly, of course. We'll see in a second. So and then we move our result becomes this temp, this node. So we're accumulating. So when we're sort of done, we merge them in reverse order. You realize that we're changing the order. First we put small guy, then second small guy. We got them, but in reverse order. So this is why this reverse linked, everybody follows this? So this is why this reverse linked is so very useful. Because then we could use it to restore things to the right order. Of course, we have to be a little careful, because we know that whatever we accumulated starts from result, ends with last one. But when we stopped, when this iteration stopped, there could be, or for sure in most cases, there is at least one list which is still not merged. Right? And what we need to do is to do this. And this conditional picks the correct one. What it says that if we exhausted the first range, use whatever was left in the second range, otherwise use whatever is used in the first range. Right? Okay, what's wrong with this code? Think complexity, don't think C++. two passes. We have to go through the thing, sort of merging it. So how many, let us think about how many set successes do we do? We do sort of n successes on the way there. There will be some tail, but usually tail will be small. You know. So we do, roughly speaking, n set successes here. And then we're going to do roughly the same number, actually, literally the same number, which is n, doing this. So we do twice as many. Any other problems? Algorithmic, never mind C++.
Tail is really large.
Huh?
You might not be able to, I mean, you're going to have to touch it all. Is there a way to?
No, you don't touch it. I mean, whatever you start with, you just, you do this. It's very hard with linked lists anyways. It's a good observation. We will encounter it when we do what it's called merge of vector of random access structures. But here it's not. Think about very simple thing. How many tests do we do per iteration? 3. Yes? One test, second test, third test. I claim that for sure this test is needed. We cannot get rid of that. I mean, this, we're doing merge, we have to compare, yes? But do we really need algorithmically, at least from general principle, to do these two tests every time through the loop? Why not? No, it's not the argument. Yes, because only the one which we moved could become empty. It's not necessarily small. I mean, yes, the one which it's small. Yeah, yes, thank you. I misunderstood. I thought you were talking about shortest. No, the smallest. You were correct. Yes. So. And now we do 2. So that, of course, requires us to think deep thoughts, which we will not think at this very moment. At this very moment, we'll have other things, because now we're almost ready to write our sorting algorithm. And of course, let us now move a little bit, sort of. First, let us look at this. This is a very simple operation. This is an operation which takes 2 lists, merges them, and returns the, we just use merge linked simple. X nil, Y nil, whatever our nil is. Nil was given to us. Right? There's no code. It's just a way of invoking our merge function, which actually has lots of arguments, has 5 arguments. And we need a binary function. Remember, for our wonderful machine. Again, here, the idea of the algorithm, and sort of, let us look at it, then I will rhapsodize for a little while. So here we come with a sort of, the whole point. What I'm doing, I actually, the purpose of what I'm trying to show you is not to teach you to sort lists. Of course, that's a useful skill. But the purpose is to show you this code. Because observe, this is the same machine as we had before. And it works like a charm. It sorts things. Somehow it manages to do it without ever dividing list by half. Sort of, if you want to see a really bad program, go and buy at least first edition of Patrick Henry Winston. I will mention the name. Introduction to Lisp Programming. And look at his algorithm for sorting lists. It possesses many remarkable properties, including the following one. It uses n log n extra storage, which is truly remarkable, sort of, for an algorithm which doesn't need, basically any extra storage whatsoever. This is an example of sort of a famous person. He's a professor at a respectable, I would say, school, publishing something just truly, truly terrible. It's also slow. Cannot argue. It's published, therefore it's good. So here we literally use our wonderful device, and what we do, we rip little lists one at a time. This is why we do this search successor. We take one guy at the very beginning of the list, rip him out by, sort of pointing him to the last, which is effectively our nil. We don't really need to know who nil is. And we throw him into the device. And what device does? He will merge him whenever needed. Again, why? So this is counter add. Remember, it's just the machine works. So we put them there. We don't know how many we put there. We don't keep the count. The counter, in some sense, represents the count. If you look at the counter, do you know how many elements are there?
All non-zeros represent 1 bit.
Yeah, it's literally, it's looking at the count, it shows you the binary number, which is the number of elements in it. So, and then we do counter reduce. Remember, we sort of carefully put them all together, and it happens by magic. In some sense, if you don't find it's beautiful, I have nothing to teach you. Right? I mean, we're not on the same wavelength. We're not, and there are people who, especially in the modern world, you meet somebody and say, oh, Bach is a great composer, and he says, Lady Gaga is much more gifted. And, it's free world. People are allowed to say whatever they like. So some people will say, oh, this is not object-oriented, or this is not functional, which it isn't. And I'm very proud of it. This counter device is not a functional device. But in some sense, my entire here, I remember I told you I'm going to be rhapsodizing a little bit. These literally, the essence of my life work, this piece of code. That's where it started. That's where it ends. I have to tell them about the fish. Did I? You know the story about the fish? No, you don't. I have to tell you about the fish. So I was young once. The year was, at that time, was 1976. It's a long time ago. Some of you were not even born. And I was a good programmer. I was writing operating systems, stuff like that, doing a good job. But I aspired to greater things. When you're young, you aspire to greater things. There was an opening in one very prestigious institute of Soviet Academy of Science to work on design of parallel computer. Oh, I wanted this job really badly. And a friend of mine who worked at this institute recommended me to this group. And I knew I'm going to go there for an interview. And I'll have to say some wonderful things or they will not give me a job. And right before my interview was scheduled, a terrible thing happened. I ate some raw fish. So, I mean, it shows you that you have to be very careful with what you eat. So I ate raw fish, and it was also very tasty, but like within 8 hours, by temperature was 103, and they had to dry. I was in a bad situation. So I'm in the hospital, flying above my bed. It happens to you when you have high fever. But what I'm thinking about is this coming interview about parallel computers. And I know nothing about parallel computers. Not now, nor ever, not at that point, but I really want the job. So I need to come out with some brilliant idea. So I'm floating above the bed in space and thinking, and then I suddenly realize how to add 4 numbers in parallel. I say, oh, I could add them in parallel if I add first 2, and then I add second 2. And I said, oh, wonderful. And I had this vision of this huge addition tree. When you're sick, amazing things come to your mind. And then I realized the second great thing, while I'm still floating, that it could be multiplication. And the same thing will work. And then I realized I cannot now tell you, but I sort of started realizing more and more functions which will work. Min will work. Max will work. Division will not work. So, and then I realized, it's good to be sick, that it has to do something which I almost forgot, this thing called abstract algebra. You say, how this relates to abstract algebra? See, I have been teaching a whole course, for those of you who remember. So I remembered that there is this thing called associativity. And I realized that this idea will work as long as the operation is associative. And that became sort of my central theme, that how could I talk about associative operations, how could I write algorithms like that. And when I came to the United States, somewhere on the way, maybe in Austria, I realized that merge was associative. For me, a very big deal, because I never even thought about merge in terms of plus and times. But merge is associative. And then I realized that I could do merge sort with the help of what I called parallel reduction. Of course, it took me a while to realize that I could do parallel reduction with the help of this device. But in some sense, that's the summary. If you want to say, Alex, what you have been doing all your life, that. Right? And you say that's not good enough, probably not. But at least that's the essence of, again, when I talk about, some of you heard the term generic programming. At least it meant something to me before it was used by some other people to designate some ugly hacking. But for me, it was this kind of programming, finding algebraic structures on which algorithms are defined and writing them like that. So in some sense, this sort of, literally, if you don't get it, we're on different wavelength. You should, and ta-da, sort of, it's actually, let me tell you, majority of people do not get it. Majority of computer scientists do not get it. And there is absolutely no indication that getting it will make you rich. Paul gets it. As far as I know, are you rich? No, he's not rich. See? So it will not make you rich. And my dear friend Dave Massey gets it. No, he's not rich either. He's doing all right, but not starving, but he's not rich. So this, but from the central point is literally the idea of finding things like that and finding how they're used. Yes? And of course, the second idea is that it would be terribly nice if using this programming at that level wouldn't cost us anything. Because anything could do beautiful if it's very, very slow. This is why they design languages such as Prolog, right? Because they don't care, as long as they could write it as horn clauses or things like that. So the combination of two things, doing it in mathematical theories and not losing efficiency, describes two pieces of wisdom which I got. Right? So, you see this piece of code? So what you will try to do, I want to really go back to actually writing code. Maybe we will eat lunch now, and they have churros. So we'll eat churros, and then we will try to do two things. We will try to, probably for about half hour, we'll try to write, or maybe 20 minutes, try to write merge which satisfies our criticism. Remember our criticism? That this was too slow. And then, for the second part of the class, after we write this merge, of course I wrote the merge. So, and you will find it in this directory, but please do not copy, it's not fair. We need to write a test. We need to see if theoretically more efficient merge will outperform a short and seemingly wasteful merge. Right? This is for, I promised experiments, so Param could be happy now. He has been criticizing me since the beginning. Not enough experiments. Not much. No experiments, yes. Right, so we will start doing experiments, all right? So, well, everybody understands the code. Please. Okay. Churros.